Okay, so welcome to today's lecture. Last time we saw the multiple access channel, inner bounds with the multiple access channel in the one-shot case. And previously we saw the point-to-point wiretap channel. Okay. So today I was thinking, what should I do? First I thought maybe I'll do broadcast, but maybe I'll do something slightly different, which is more illustrative of the techniques. So what I'll do instead is the multiple access wiretap channel. So we'll combine wiretap and multiple access channel. Let me refresh page. Just a second to answer the door.
Pranab, you are muted. We can't hear anything you're saying. Yeah, everything you said while drawing things, nothing was audible.
Okay. I'll repeat that. Okay, so we are going to do the multiple access wiretap channel. And I chose this channel because it's a nice illustration of everything that you've learned so far, both packing lemma and covering lemma. In fact, we'll have to strengthen the covering lemma, but we'll do it as the time comes. Okay, so the setup is the same as that of the good old multiple access channel. There is Alice and Bob. Alice has a message M that she wants to send. Bob has a message N that he wants to send. Okay. Then Alice uses a private coin encoding algorithm and encodes message M into a probability distribution over code words X. Bob encodes message N into a probability distribution over code words Y, independent of Alice. Now X, comma Y is inputted into the channel. Now the channel produces a probability distribution on the output symbol Z, but because we are in the wiretap scenario, we will assume that the channel has another output, which is the side information of the environment, okay, formalized by the symbol E. So the channel characteristic is given by this condition probability distribution, probability of
W given, oh, Z, you're using Z. Okay.
Probability of Z E given X point. Okay. This is the channel. And now, of course, the Charlie, which is a legitimate receiver, he gets a sample from Z, and then he passes it to a decoding algorithm, and the output of it, it's again a private key decoding algorithm, the output of it is his guess M hat, comma, N hat.
Wait, what do you mean a sample? You get a joint state on ZE, right? Oh, sorry. This is not quantum. Sorry.
The legitimate receiver will always get a sample from Z.
Okay. No. For a moment, I confused it with quantum. Sorry.
Yeah. So the E goes to the eavesdropper. Okay. And what we require that for every M, comma N, the probability distribution that E sees, okay? So we can model it by P of E given Mn. Okay? This should be approximately equal to the margin on E. So for every pair M, N, the resulting probability distribution at the eavesdropper is almost independent of M. Okay, this is the secrecy criterion, and the correctness criterion is probability that N hat is not equal to Mn should be less than epsilon. Note that the correctness criterion is given in the average case setting as in the MAC, but the secrecy criterion is in the worst case setting. So let me write this down.
Pranav, I have a question.
Yeah, you can say, but I'll have to keep writing. Yeah.
Yeah.
Okay.
So even in the wiretap case, I forget the Mac. Even in the wiretap case, we always derive secrecy in the worst case setting, as you just said, for all messages. Suppose I weakened the secrecy condition to the average case. Okay. So is it known whether one can get better rates in that case?
No, the same thing.
The same thing. Okay.
Yeah. Okay. Yeah. So any questions about the definition of the model? Okay, if not, let's proceed. So from our study of the multiple access channel and the wiretap channel, we know what to do out here. So we'll start off with random codebook construction as before. So random codebook. So Alice will generate samples x1, x2 like this. So x, so it will be 2 raised to r1 plus r1, right? So in the wiretap channel, if you want rate capital R, the number of code words in our code book is 2 to the capital R plus small r. So now, of course, we have a pair of rates, capital R1, capital R2. So correspondingly, we'll have small r1, small r2. And we'll do the usual thing. We will divide this sequence into blocks of size 2 to the little r1. Okay. And so this is for Alice. So body, in fact, IID. Bob does the same thing. Okay. Why is this pointer coming? Okay. So Bob does Y1, Y2. And this is now broken up into blocks of size 2 to the R2. Like this. So this is IID from P1. Okay. So then again, you we fix probability distributions PXPS. So I should write that somewhere. Okay. So fix input probability distribution PXPO, and then there will be a union over all PXPO, okay, in order to get the set of all achievable weights. Okay, so once you fix the input probability distribution Px and Py, then the joint probability distribution is fixed. So it is Px, Py, and then the operation of channel. So that is Pze given Xy. Okay, so this is the joint probability distribution under which we will be calculating all our mutual informations. Okay. So now the same thing. If Alice has to send the message M, so she goes to the mth block out here. So let us say this is the mth block. Okay. So there are 2 to the capital R blocks, which is fine. And then Alice picks a random code word in the mth block and inputs it to the channel. And Bob does the same thing. In order to send the nth message, he goes to the nth block, picks a random code word within the nth block, and inputs it to the channel. Okay. So this is good. So now for correctness, we know what is the criteria. So for correctness, we'll require that Charlie should be able to decode the actual code word that was sent. So sure, Charlie is only interested in the block numbers, but just as in the wiretap channel, we require that Charlie decode the actual code word that is sent. And I mean, once you do a deeper study of the proof, you will see that this proof technique does not do anything better if all that we require is decoding the block number. Okay. So if you're following this strategy, then you might as well decode even the code word that was sent. Okay. So Charlie decodes actual pair of code words. Okay. So if and only, so the constant the rates we know from what we did in the last class on that. So R1 plus R1 is less than mutual information of X with ZY under P, then constraint R2 plus R2. For the correctness part, we're just ignoring Eve and applying what we had studied in the last class. And as long as the rates, the capital R and the smaller rates satisfy this constraint, Charlie can decode the actual pair of code words. So correctness is solved. Is this clear so far?
Yeah.
Okay. So let's go ahead. Now, the interesting thing is the secrecy part. And this is where it will turn out that we have to do some extra work, okay, on the covering limit. So let us see. So let us try to guess what we require. So let me go back also. So for the secrecy part, we'll look at Alice, Bob, Channel, and Eve out here. Now, if you go back to the wiretap case, the point-to-point wiretap case, then we had done the secrecy analysis by the covering lemma. And what did we obtain there? So remember, we are averaging over a block of size 2 to the R1. Okay, for Alice. Let us ignore Bob for now. If you're just looking at the channel from Alice to Eve, Alice is randomizing over a block of size 2 to the R1. And we want that the probability distribution that Eve sees should be almost independent of the block numbers. Okay, should be very close to the marginal probability distribution. So, we know from the good old covering lemma that so let me So, okay, now we have, let me put in the smooth rates out here. This is I min epsilon, okay, and this is I min epsilon, and this should become I max epsilon, okay. So, if we completely ignore Bob, okay, and all we require is that Alice's message be secret from E. We require small r1 to be larger than the max mutual information from X to E, okay, under the probability distribution. Now, similarly, if we ignore Alice and just concentrate on Bob, we'll get the analogous requirement. Okay. So we require this. But actually, I mean, we don't want individual secrecy, we want joint secrecy. Okay. So if all we wanted was individual secrecy, then this is good enough. So individual secrecy means that averaged over the messages of Bob, Alice's message is secret. Okay. Vice versa, averaged over the messages of Alice, Bob's message is secret. But this does not mean that given a pair m comma n, the message is secret for me. Okay. So what we really want is joint secrecy. So this is individual secrecy. So to achieve joint secrecy, of course, we should have individual secrecy, but we need to have more. So for example, let me give a concrete example how this may arise. Let us say Eve's random variable is just 2 bits, okay? And it so happens that the probability distribution that Eve sees, okay, is the following. So each bit is uniformly random, but the 2 bits are the same. Okay. So
no, sorry, I don't get the example. Can you repeat that, please?
So as you average over Bob's messages n, okay, Eve sees uniform probability distribution on hard bit. Okay. Sorry. So what did I say? 2 bits. No. So
No, Pranav, I don't understand the setup.
I want the setup is I want to show that individual secrecy does not imply joint secrecy. Okay. So suppose you have a toy example that if you average over the messages n, okay, you get a uniform bit at each end. Okay. And similarly, if you average is over Alice's messages, you get a uniform bit. Okay. But if you look at a fixed message m comma n, then you get a fixed bit. Okay. So Eve's random variable is just 1 bit. And for m comma n, Eve's variable is deterministically fixed. Let us say it's either 1 or 0. So for some pairs m comma n, Eve's bit is 1. For other pairs m comma n, Eve's bit is 0. But the distribution of ones and zeros in the rectangle for m comma n is as follows. Like if you fix m and average over n, so that means you fix a row number and you fix row number n, look at all the entries in that row. So all the entries in each row have equal number of zeros and ones. Okay, this is what I want to say. So think of a rectangle of size m times n. Okay. Each row has an equal number of zeros and ones. Each column has an equal number of zeros and ones. So that is enough for individual secrecy, which means that hold Alice's message fixed at n, average over Bob's messages. Okay. So then Eve sees a uniformly random. All this means is that the number of zeros and ones in each row is equal. And similarly, if you fix Bob's message and Alice average over Alice's message, this means that the number of ones in every column is equal. Okay, but if you look at a particular m comma n, the bit of Eve is determined. Okay, so by looking at that bit, Eve knows whether m comma n is in the first set or in the second set. So there is a loss of secrecy. Okay, there's a loss of joint secrecy, but there is no loss of individual secrecy. This is what I want to say. So what we really want here is joint secrecy. Okay, and these two conditions that I've written are not enough to guarantee joint secrecy. So is this argument clear?
Basically, so you have the m cross n thing, right? So what you're saying is that even if you have bit vectors on both rows and columns, which have the same number of ones and zeros, that does not imply that the distribution of ones on the entire grid is not uniform in some sense. As in there might be a concentration of ones on one side, there might be a concentration of zeros on the other side, and something like that.
No, nothing so complicated. So let each random variable be just 1 bit.
Okay.
So then, and I'm also saying that for a m comma n, each bit is fixed. Okay, for some m comma n is fixed to ones, others fixed to 0.
So this is the channel. This is the channel.
This is a channel. This is a channel from Alice Bob to Eve.
Oh, you're saying for some m comma n fix it to 1, for some m comma n fix it to 0.
That's all. That's all.
And so, if Eve sees that bit, she can tell that this m comma n came from this part of the matrix. And
yes. Okay. Yes. So there is a loss of secrecy.
Yeah.
Okay. There is one bit loss of secrecy because of Eve. Okay. But this is loss of joint secrecy because Eve knows that m comma n is from the first set or the second set.
Right.
But there is no loss of individual secrecy because every row has equal number of zeros and ones. Every column has equal number of zeros and ones.
Secret keeping is another, the Shamir Wala protocol. That is another good example, right? Individuals.
Well, yeah, there are lots of examples, but I came up with maybe arguably the simplest example. Okay, so I mean, if you want to think of it as a rectangle, because I mean, Eve is just 1 bit, deterministic fixed by m comma n. So think of it as a rectangle, okay, indexed by the rows are indexed by n, columns are indexed by n, okay, and the mth entry is either 0 or 1. Okay, it's a rectangle filled with bits. And once you have a rectangle filled with bits, there is a loss of joint secrecy. But there may not be a loss of individual secrecy if every row is balanced and every column is balanced. That's all I'm saying. Okay. Is the example clear?
Yeah, to me, yes.
Yeah, Hari?
So conditioned on the fact that Eve is receiving certain bit, the distribution on the rectangle gives away the secrecy. Is that what is being said?
Yeah. So, I mean, if she is that her bit is 1, she knows that this is from one half of the rectangle. I mean, the half. I mean, the half is scattered all over the rectangle, of course, but she knows it's the half such that m comma n is maps to 1. Okay, and if she sees the bit is 0, she knows it's from the other half of the rectangle.
Yeah. Okay.
That's all. So, but I mean, it's scattered well enough such that each row has equal number of zeros and ones. That's what I mean by balance. Each column is balanced.
So there is a question of whether such matrices exist, but I think probabilistic
there are
method
lots
will
of such matrices.
Yeah.
No. Yeah. I mean, probabilistic method will give an almost balanced thing, which is also good enough. But you can also construct a few examples, right? At least for small numbers. So you can convince them that there are lots of such examples.
For 2 cross 2, it's the identity or the NOT gate is such an example, right?
Is one such thing. Yeah. The identity matrix is one such example. If it's 2 cross 2. Okay, and if it's 4 cross 4 also, you can cook something up. Okay. You can replace the identity by the all ones matrix, for example. There are tons of examples. A little bit of thought will show you that it's fairly easy to find examples like this. Okay, so yeah, but I mean, that's not the main point. The main point is individual secrecy does not imply joint secrecy. Now, what we really want in the wiretap thing is joint secrecy. So we'll need an extra condition, which you cannot guess. So let us say if Alice and Bob got together, okay, I mean, they behave independently in the setup, but suppose they got together and I want, remember, I want joint secrecy. I want m comma n to be unknown to E. Okay. Now, let us say Alice and Bob got together and did, this encoding jointly. I still want Eve not to know what m comma n is. So now let us see. So Alice was randomizing over a block of length 2 to the R1. Bob was randomizing over a block of length 2 to the R2. Now Alice and Bob get together and they're independently randomizing over the block. So you can instead say that the relevant part of Alice and Bob's operations are in a rectangle. Okay. So this rectangle is the Cartesian product of Alice's block and Bob's block. So now if Alice and Bob are randomizing over a rectangle, the resulting distribution at each end should be almost independent of the rectangle number. So I think it will help to draw some picture here. So this is Alice's block. Okay. So we are looking at the mth block. And the columns of this matrix are indexed by Bob's block. Okay, this is the nth block. Now, choosing Alice's operation is choose a random element from her block. So that is a random row of the rectangle. Bob chooses a random row number, column number of the rectangle. Okay, and random row number, random column number. So let us say Alice has sent the ith element of her block. So this is the ith row, and Bob has sent the jth element of his block. So this is the jth column. So what is the So what is the probability distribution at if z? Okay. So this is, so I can say this is 1 over 2 to the R1 plus R2. Okay. And then this is probability E given. So xi, yj. Okay, so of course this is the mth block and the nth block, but okay, and then there is a sum over I j. So let me write. What's wrong with this? Let's say xmi, y, and j. Maybe this is the best. Okay. So the probability distribution at if C's is the probability distribution E given xmi. So xmi is the ith code word in the mth block for Alice, and y and j is the jth code word in the nth block for Bob. Okay, and we are doing a uniform average. Okay, so this is, you can think of it as the average of the rectangle, and we want this to be close to the joint distribution. Sorry, this to be close to the marginal distribution on E. So we know what is required for this. Okay, so let me write down and then I'll comment on that. Yeah. So I want R1 plus R2 greater than So let me explain what this means. Yeah. So, okay, I wrote something, but I mean, there's a catch to it. So let me explain to you why the catch is there. So at first it looks okay. So this is like the statement of the good old covering lemma that I have a probability distribution, joint probability distribution between an input and output. Let me think of the input as the pair xy, the random variable pair xy. That's not a problem. The output is E. So I'm looking at a joint system on xy on one end and E on the other hand. And I want to take the sample average of conditional probability distributions on E. Okay. Condition on samples taken from xy. I'll take the sample average, which is out here. And this should be equal or almost equal to the marginal distribution. It's so good. So far, so good. Only thing is that the covering lemma, the original covering lemma required these samples to be independent. But now if you look at this, these samples are not independent. So, okay, so how many samples I'm averaging? What? 2 to the R1 plus R. But actually, this 2 to the R1 plus R2 samples are not all independent, as you can see. They are pairwise independent, but they are not fully independent, because if I
they're
look
not
at,
even pairwise independent, right? Along a single row, they are not pairwise independent. Even that is
you are right. Actually, you are right. You're not even pairwise independent. Yeah, yeah. So if you look at another pair I prime comma j prime, Then let's see. So yeah. If I look at another pair, I prime comma J prime. Okay. So this and this is what we're talking about. Okay. So the probability distribution of E conditioned on Ij, and the probability distribution of E prime considered on Ij on I prime J prime. So these are pairwise independent. Okay, if I prime J prime is different from Ij, but let us say I is equal to I prime, but J is different from J prime. Then they are not independent. Okay, so there is limited independence, but again, I mean, it's not even full pairwise independence. Full pairwise independence would have required that take any two samples, I, J, and an arbitrary I prime, J prime. The conditional probability distributions are independent, but that's not the case. Okay, so there is a large degree of two-wise independence, but not every pair is independent. So that's the scenario we are working on. Okay, whereas the covering lemma that we studied assumed that all these 2 to the R1 plus R2 samples should have been independent. Okay, not just pairwise independent, but fully independent. Under those settings, we have proved the covering lemma. So actually, I mean, you can the covering lemma is proved under convex split. So you can observe that the proof of convex split even works for pairwise independence. So you can say that, oh, maybe I can apply that, but as Shantan pointed out, I don't have genuine pairwise independence here because there are pairs that share row numbers or column numbers which are not independent. So I cannot even apply that. So actually I have to prove a new covering lemma for this. But anyway, to get an idea of what to prove, I still expect that fine. There is a large degree of pairwise independence, so the good old covering lemma should work. So some constraint like so the constraint like what I wrote here, R1 plus R2 is larger than I epsilon max between the input random variable xy and the output random variable e should work. So this is the kind of statement we'd like to prove, and this is what we will do in the rest of this lecture. So we have to prove a new covering lemma, which is exactly like this. Okay, and this covering lemma is tailor-made for our Mac wiretap application. So to emphasize, like, I mean, what will be the form of the statement we are trying to prove? So we will say that we have like 2 to the R1 samples coming from PX, 2 to the R2 samples coming from PY, then condition on XI and YJ, we have a probability distribution on PE, and I do this kind of average. Okay, and I want the sample average under this kind of averaging should be close to the marginal P. So what are the bounds on R1 and R2 such that this works out? And the claim is that bounds on R1 and R2, like these 3 bounds on R1 and R2 together will suffice. So is the issue clear? And what we are going to prove and on what settings are you going to prove? Is that clear?
I just have a comment, maybe not related to this particular version of the lemma, but to the other version that we know. So this pairwise independence thing really shows up in that proof, in the successive cancellation style proof, because essentially you write a tripartite convex split lemma state, and in that you're averaging over single like xi prime and all that, right? But there you need the rate to be higher. There you need the rate to be higher than the individual rate. And that is precisely what gets you the average state, at least on the X system. And then you can take a triangle inequality and do the averaging on the Y system also.
Oh, that is successive cancellation.
That is successive cancellation. That's what I said. But I mean, you can really see where you have to put in more randomness right?
Okay.
To counter this not strictly pairwise independence business. You can really see where that trade goes.
Mhm. Yeah, yeah. So hopefully these things will, at least some of these things will become clear. So anyway, but before we go to that, Hari, is the issue clear?
Yes, yes.
Yeah, what we are trying to prove? Good. So let's see. Okay, so remember we prove our covering lemmas by proving convex split lemmas. So actually what we'll prove is what is known as a tripartite convex split lemma. Okay, and from there we'll infer the covering lemma that we want. So the tripartite convex split lemma, as Shanton pointed, is slightly more general statement, and I mean he pointed out nice features of that. First, let me write down the statement. So remember, as usual, there is an underlying probability distribution, joint probability distribution that we like. Okay, it is on PXY. So it's called tripartite because there are three systems involved. PXY. Now, the original convex split lemma has two systems involved. So that should have been called bipartite, but unfortunately, the authors wrote a different paper with a different joint probability distribution and called that bipartite. So that's why in my lectures I called it unipartite. Anyway, so don't bother too much about nomenclature, but like with experience, you will see why unipartite, bipartite, and tripartite sort of make sense. Okay. Anyway, so we have a joint probability distribution XY, and in the actual statement of the tripartite convex split lemma, it can be any joint probability distribution. In our wiretap Mac, the probability distribution that we are working on out here, right? So we are working on. Okay. So I mean, this kind of probability distribution we're working on, or this kind of setup we are working on. So remember, X and Y were independent, right? Because M came independently, N came independently, the private code algorithm is independent. So X and Y are independent. And our control probability distribution, which I wrote explicitly, it is Px times Py. So for the purpose of the wiretap multiple axis channel, we are looking not at arbitrary probability distributions on XYE, but special kind where X and Y are independent. And then E has a probability distribution depending on the pair XY. So that's a slightly weaker regard, but anyway, the full tripartite convex split lemma, which is, I mean, as easy or as difficult to prove as our covering lemma, will work for the most general class of probability distribution. So X and Y can be dependent also. Okay. So that's so as usual, on one side, I have the complete product distribution. So it is Px1 times so 2 to the R1 independent copies coming from X. Now the Y is also there. So okay. So 2 to the little R1 independent copies of X, 2 to the R2 independent copies of Y. So this is the size of Alice's Bob's block, as you can see, all that is there. And then finally, we have the marginal U. So this is one end. So this will be approximately equal to. Okay. So the aim of convex split is to introduce correlation between X, Y, and E in one position and leave the others untouched. Okay, and this one position will vary uniformly between among the set of all positions. So what do I mean? So the set of all positions now is rectangle, right? I mean, there are 2 to the R1 X's, 2 to the R2 Y's, and we imagine them as a rectangle. You can draw the rectangle. Keep reminding you. So this is 2 to the R1. This is 2 to the R2. This is the X1. It's 2 to the R1. This is Y1, Y2 to the R2. So these are the sample. And now I want to correlate the like one such coordinate. So, and I will take the sample average. Okay. So I picked a coordinate I comma j. Okay, and I want to correlate that. So I look at the joint distribution between xi, yj, and I've correlated that, and now I leave the others untouched. So I'll write short form. I'll write px minus I. Minus I means this is px1 times px2 dot dot. I just drop xi out here, and I have pxi1 times and so on and so forth. Okay. So it's in product with px minus I, py minus 2. So if, of course, there's some guarantees which I'm going to write. So is this statement clear? Like I've correlated the ijth coordinate. Okay. So not only I've correlated it to E, I've also correlated the x and y together. Okay, so xi, yj, e. These three random variables are correlated according to my favorite distribution pxy. And the others are left untouched in tensor product. Okay, just product of their margins. So if so, the condition is so let me write now suggested notation. So it is a joint distribution pxye, whatever it is, with respect to the tensor product of the margins, px, py. Okay, so let me show. So is this statement clear to everybody? So this is the kind of statement I'll try to prove, that if the rates satisfy this. Okay, so note the lower one, the sum rate R1 plus R2. So normally I would have liked to write it as a mutual information kind of thing. But if and in fact in the covering lemma I did write it as a mutual information. Right? So I wrote it as I max epsilon xy to e. So if x and y are independent, these two terms are the same, right? So what was I max epsilon xy e? It was d max epsilon of the joint distribution with respect to product of the margins. Okay, so what would that be? It is d max epsilon of the joint distribution pxye product of the marginals. But if I'm talking of the mutual information with a margin on xy times the margin on e, and there because x and y are independent, the margin on xy it is of the form px times py, okay, and times p is there. So this quantity is equal to I max epsilon if x and y are independent. But the tripartite convex split lemma is a more general statement. So even if x and y have dependencies amongst them, correlation amongst them, this statement still holds that R1 plus R2 has to be larger than d max epsilon of the joint random variable with respect to product of the three margins. Is the statement clear of the tripartite convex split? Okay. So then we go ahead. Yeah. But before going ahead, let me point out what is the IID limit. Okay. So the IID limit so this is what you'd expect. R1 is larger than Shannon mutual information. And R2. So this is like when you talk about the IID limit, so you have to divide by F, right? the limit path channel use. And R1 plus R2. Okay, so the D max epsilon will go to D, the Shannon relative entropy. And you can evaluate what that D is. It turns out to have very nice interpretation in Shannon theory. So it will be XY E plus mutual information of XY. Okay. So note that again as a remark, if X and Y are independent, mutual information of XY is 0, and we get what we expected, that R1 plus R2 is greater than the mutual information between Xi on one side and E on the other side. But the more general statement looks like this. So you can go home and check that if you look at the Shannon relative entropy of these two probability distributions, you actually get this exactly. So now let's proceed. Let's try to prove this. So the proof technique is very similar to that of the unipartite convex split lemma that we studied earlier. Okay. So let me write. So we will show that the Shannon relative entropy on the right hand side. So the right hand side is so this is the oops sorry. Yeah, I've read the convex split. So E Xi Yj E times Ex minus I times E Y minus. So this is the convex split state. So that is the first state in the relative entropy expression. Second state is the so let me write it as Px to the R1. This is the tensor product of all the Px's, Py 2 to the R2 of them. So we'll show that this quantity is less than epsilon square. And then by Pinsker, it shows that the two probability distributions are epsilon close in the L1. Correct? So the same strategy as in the proof of unipartite convex. Any questions so far about about the definitions of the states? About the definition of convex split state? No? So let's go ahead. So we continue, same strategy. So D we know this is equal to the average of relative entropies. So what was the expression? So it is the average state, and then yeah. So let me just check this. Let me just check the correct form of this. Yeah. So yeah. So let me So I just verified it. Yeah. So this is pick out the ith state in this expression. So this is pxi, ijth state, y tensor x minus I, tensor y minus j. Then with respect to the product state, then minus so again the ijth state. So this is the convex split state. Okay, so not writing this one. So we have this decomposition rule for entropy. If you recall the proof of the convex field lemma, this was the first step, that relative entropy. So let me write down. Maybe Okay, so I mean, there are three states. There's a convex split state, then there is the fully independent state, and then there is the average of, and then the convex split state was the average. So, and then there are the individual states. Okay, individual states. So the convex split state is an average of the individual states. So the convex split with respect to fully independent. So this is the final thing that we want to show. This is small, fully independent. So this is equal to the average. Here is the uniform average. So this will be like if there were n of them, so it will be d of like ith state with respect to fully independent. Okay. Minus d of ith state with respect to convex split. Okay. So this is the decomposition rule for relative entropy, and this is exactly what we have applied. Okay. So convex split state, fully independent state. So that is equal to the average. So this is the ith individual state with respect to fully independent state minus ith individual state with respect to convex split state. Now, well, let us look at the first term out. So first term,
Pranav, can you scroll up just one page? Just one page.
like this.
Yes.
Yeah.
Okay. So
So it's convex split state, and this is the fully independent state.
So R1, R2, you have already said.
Yeah. So
No, I just want to see where the thing will appear. Okay.
okay.
See,
So
here's my question. So we proved convex split, right? And we proved the smoothed version of the convex split, right?
what's smoother one? No. So let me do this. Okay, so just one. Okay, so let me look at the second term first. Yeah, that is easier to handle. So let's handle the second term. So this is E P xi yj E. Tensor product P x minus I tensor P y minus j convex split. So So by data processing inequality, this is less than, okay, this is this is greater than d p xi yj e, okay, with respect to what I get by discarding x minus I and y minus j of convex split. So let us see what that is. Okay. So let's write discard convex. So I want to discard this. Okay. So I mean, this is good for us because data processing says that the left hand side is greater than the right hand side, but now there's a minus sign out here. So when I plug it back out here, I'll get an upper bound. Remember, finally, I wanted an upper bound on this point. I wanted to say that this is less than epsilon square. So things will be going in the right direction. But let us understand what discarding xi y minus j of convex split looks like. Okay. So convex split state had these terms like, so there was this term p xi yj e times p x minus I. Yeah, I'm not looking at a fixed yj, p y minus j. So there was one such term like this, which, and all this occurs with probability. I mean, sample error. So this term was there. Then there was another term or a bunch of terms. So these terms arise from j not, let us say j prime not equal to j. So that is pxi, okay, so yj prime e tensor px minus I tensor py minus j. Okay, so remember the convex split state was what? Like choose a I prime j prime from the sample, from the rectangle, correlate xi prime, yj prime, and e together, and keep the rest in tensor product. So now we are concentrating on a fixed pair I comma j. So this, I mean, this is the fixed pair I comma j. We are concentrating on that, and you will discard the remaining registers. For that, you have to understand what the convex split state looks like with respect to this fixed registers I comma j, xi comma yj. Okay, so the ijth element of the convex split is exactly what we want. So it is this. I'm now looking at, so these are the I j prime element. Okay, so this is the I j prime term. I j prime term. Okay. And that's why the sum over j prime not equal to j. So similarly, there will be sum over I prime not equal to I. So it will be p x I prime yj tensor p x I prime removed p y minus j. So this is I prime j term. And then there are the others, that I prime not equal to I, j prime not equal to j. So these are the I prime j prime terms. So this is the full convex split state with close brackets. So I've broken up the convex state into sum of 4 terms. So there is the xi, yj, which are interested in. Then these are the ij prime terms. These are the I prime j terms, and these are the I prime j prime terms. So is this way of writing the convex state clear to everybody? Yes. This is the key step. Hari? Clear?
So like towards the end, like
sorry, come again. I didn't get you.
yeah, like towards the end, which term are we splitting? Like
No. So this whole thing between these two big brackets. So let me show. This whole thing between these two big brackets is the convex state. Remember, the convex state was an average of 2 to the R1 plus R2 terms.
Yeah.
Right. So I'm just writing that average. I'm grouping terms together depending upon ij. So there is the ijth term. I mean, fix a I, fix a j. I mean, that is a fixed ij against which we are applying the data processing inequality.
Yeah.
Okay, this is the ij from this summation. This ij and the summing variable I prime j prime here are different. Okay. So I'm analyzing the second term out here. This is the convex split state. Convex split state by definition is an average over I prime j prime ranging from ranging up to 2 to the R1 and 2 to the R2. Okay. So this convex split state I'm now writing in a more detailed form. So this is the ijth term in that decomposition. These are the ij prime terms in the decomposition. Okay. So the I coordinate is fixed to my favorite I out here, but j prime is different from my favorite. Then there are those terms which look like I prime j. So j is this fixed j from outside, my favorite j, and these are the I primes which are different from us. And finally, so most of the terms are of course here. Finally, these are I prime j prime, where I prime is not equal to I and j prime is not equal to my favorite j. So that's all I've written.
Yeah.
Okay. So nothing new. I mean, this is the equality. Okay. Next. So now remember, I want to discard x minus I and y minus j. This fixed. I mean, this is for the my favorite ing. So discarding that will give me a state which looks like this. So it will be 2 to the minus R1 plus R2. So now discard x minus I, y minus j. So on the first term, discarding x minus I, y minus j is clear. What do I get? I get xi, yj e plus. So here, if I discard x minus I, y minus j. Okay. So I discard x minus I, fine. All these registers go away, no problem. I am discarding y minus j. So I'm discarding everything other than yj. In particular, I'm discarding yj prime out here. Okay. And so somewhere there's a yj here, which I have to keep. So what I mean is this state will look like P. So I keep xi. I discard y j prime because j prime is in minus j. E remains tensor. Okay. So I have to discard every x minus I. So that goes away. Now I'm discarding y minus j. So yj remains. So this will be P yj. Is this step clear? So this is the key. So from here, see what I'm throwing away, x minus I, so this goes away. Then I'm throwing away everything other than yj. So in particular, yj prime is thrown away. So now I get xie out here, as correlated. And it's still not enough. I have to throw everything other than yj. Remember, there's a yj somewhere here. This y minus j prime includes yj. So that yj is here, but that's in tensor product. Okay, for this. And everything else is discarded. Is it clear, Hari?
Yeah.
So this will be y j e tensor p xi. Okay, and then finally so lastly, I mean, I'm keeping xi yj, discarding everything. Remember, this is y prime, this was j prime. Okay. So I'm only keeping xi yj. So xi prime yj prime goes away. So what remains is just p. Okay. So tensor, there is a this is x minus I prime, but there's a xi sitting there, so that remains. Everything else goes away. Similarly, this is y minus j prime. Oh, sorry. I think I goofed in the wrong. This is the third term, not the fourth. So this as written is correct. I think everything is correct. X I prime y j e. Sorry, I should have been looking out here. Yeah. So this is x I prime y j prime. They go away because it's minus I minus j. Only p survives. This is x minus I prime. So remember, there's a xi sitting somewhere there. That survives. Everything else goes away. And there's yj sitting there. That survives. Everything else goes. So this is the final expression. Okay. I hope I got this correct. Any questions about that? So this is the convex fluid state obtained by discarding everything other than xi, everything other than yj. Okay. So now, okay. So further questions, is it clear? Okay. So now I'll be applying inequality. So now, as in the proof of the convex fluid, I'll be applying inequalities and probability distribution. So what do I know? I know that Pxi yje. So this is a joint distribution. So that divided by that divided by the product of the marginals is the quantity 2 to the d max. So let's work with d max. Then the epsilon smoothing we will bring in later. So remember, so what I know that P x y e is less than 2 to the d max P x times P y times P, right? I mean, this was from the definition of d max. And similarly, I have P x e is less than 2 to the I max x colon e of Px times P. Right? From the definition of IMAX. And similarly, I have the thing on PY. So right now I'm talking with the non-smooth quantities. So I bring that out here. So this will be less than 2 to the d max Px, Pxi times. So actually that will be common. So let me write it more compactly. So 2 to the d max. Okay. So now what is this? This is Pxi. So I mean, this is of the form Pxc. Apply the inequality, okay, on probability vectors 2 to the I max xc and then Px times P. So I can write it as 2 to the I max. This is 2 to the I max. Okay. And of course, this is 1. And all this I'm now upper bounding by the probability vector Px, Py. Okay. So this is the key step. Right? So repeat, how did you get it? So this was a probability distribution on x, y, e. I upper bounded it by 2 to the d max times the probability distribution Px times Py times P. Okay? Just by definition of d max. This was a joint distribution xc. I upper bounded by 2 to the I max, okay, times the probability vector Px multiplied by P. Okay, and then there is this times Py hanging around for free. So I still get this. And then similarly, for this, with a joint distribution YE, I make the joint distribution a product distribution Py times PE. There's Px hanging out here, so I get this. But the price I pay is after multiply by the scale factor 2 to the I max YE. And here the scale factor is 1 because it's already product distribution. Is this part clear to everybody? Yeah. Hari, is it clear?
Yes.
Yeah, good. So now, so we are back to Pinsker. So remember what we had was D, convex split. With respect to fully product state. So this one was the average. So this is the ith term in the convex split with respect to product state minus the ith term with respect to convex split state. So far it was equality, no loss. But now we'll apply data processing. So this is 2 to the minus R1 plus R2, some ij, b. Okay. Now, another thing, so let me write it out here. So this was there earlier also in our uniparted convex split. So what is the ith term? So here, of course, is the ijth term. So let us write it. So that is pxi yj e tensor product px minus I tensor product py minus j. And this is the fully product state. So this was pxi times yj times PE times, of course, fully product state. So it's product on the remaining registers, X minus I, product Y minus. Right? So this was the fully product state. But now the Shannon relative entropy of this, I know what it is. So I mean this Px minus I, Py minus j is common to both. So in the ratios they cancel. So it's just xi, yj, e. That's all that matters. So all I'm saying is that the first part was equality. So let me write down. So this is equal to d p x y e px times py times p. So this part is equality, but the second part, so in this decon, the second part was an inequality, but it goes in the right direction for us. So let me write down. So this is d p x y e px times Py times P. Okay. Minus, so now I will write the lower bound that I had in the previous page. Okay. Yeah. So this lower bound, so it was an upper bound here, but this was an upper bound on the probability vectors. So what do I know? So the convex split state after discarding x minus I, y minus j is upper bounded by this quantity. Okay, and we have to look at the Shannon relative entropy between d p xi yje joint state and the convex split state after the discarding. Okay, so the second probability vector I have upper bounded by another probability vector with a scale factor. So this means that this Shannon relative entropy will be further lower bounded, right? Because I'm increasing the vector for the second argument. So that occurs as a denominator in the ratio. So what I want to say simply is d p x y e. And what was the upper bound on the convex split state? It was this quantity, which was putting in brackets times px times py times p. Okay. This was the second argument, the convex split state with x minus I, y minus I discarded. So the vector was px times py times p, but there was a big scale factor out here. Okay. So that's precisely what I've written out here. Okay. So I have the scale factor times this. Now, if I'm looking at the relative entropy between two positive vectors and there's a scale factor here, you can pull that scale factor out. So I can further say that this is equal to 2 to the minus R1 plus R2. Okay, minus this will be the same d px y px y e px times py times p. So that is this part, and then the scale factor, which will now appear as a logarithm, plus log of this. Okay, is this part clear to everybody? Yeah. So that's it. So these two terms cancel as before, and it's a log of the scale factor, which we wanted to be less than epsilon square. Okay, so let me write log of, so the scale factor was 2 to the d max as okay, I think I wrote the scale factor. So scale factor was this in brackets divided by 2 to the minus R1 plus. So yes. So this was 2 to the I max x colon e plus 2 to the I max y colon plus 1. Okay. Divided by 2 to the R. So this is the scale factor that we have. So this should be less than epsilon square for this two. So this gives constraints on the rates R1 and R2. And if those constraints satisfy, this will be less than epsilon square. So let us see what those constraints are. Okay. So remember what constraint we had. We know that R1 was larger than 2 to the I max XE. And we have to put in, so I mean, that was sloppy statement because I had ignored this log 1 by epsilon terms. So, sorry, so not R1, but I was thinking of the other. So R1 is I max XE plus something like log 1 by epsilon. Okay. So what is this telling me? This is telling me that 2 to the I max XE is less than epsilon times 2 to the R1. Okay. And similarly for I max Y. So the left hand side. So the left hand side now becomes. Oops.
Pranam, you have stopped sharing screen.
Yeah, yes. Somehow external went off. Yeah. Recovered that. So external exited. Yeah. Can you see the screen now?
Yeah.
Yeah. So left hand side. So what is it? So now I can say that it's less than now. So what did I have? I had 2 to the scroll up a little bit. Yeah. So 2 to the D max. So by the same argument, this is less than 2 to the R1 plus R2 times epsilon. This is okay, less than 2 to the R1 epsilon, 2 to the R2 epsilon plus 1. Okay. And then this whole thing should be less than 2 to the R1. Now you can see, okay, so maybe I'll make everything epsilon squared here, and this is 2 log 1 epsilon squared. So if you do all this, you can conclude that this is less than something like epsilon. So that I mean fixes the requirement. I have ended up showing that the Shannon relative entropy between the convex state and the fully product state is less than epsilon square. So this shows that what we shown that B convex split product is less than epsilon square. So then by Pinsker, convex split is close to product state. Okay. So that would be the proof of the tripartite convex split lemma. But what are the remaining issues? So I had made the statement out here. Okay. So if you see, I mean, 12 comes naturally, but I had made the statement with the smooth Dmax quantities. Whereas in the proof, I just use the non-smooth ones. But that's not very difficult. So what I have to do? I have to do something similar to what I did in the unipartite covering lemma. So let's start off with this one. So if I want Dmax f this quantity, so of course I cannot work with the original joint distribution Pxye. I have to perturb it to some P prime. Okay, so I have to basically like perturb Pxye. So this is the proof, of course. I mean, not in the protocol. To some P prime xye. So with the property that Dmax P prime on xye with respect to the second state is equal to the Dmax epsilon for the unperturbed states Pxye. So this is perturbing with respect to the third constraint. Similarly, you can perturb the distribution on y for the second, distribution xc for the first. The point is, these three perturbations are different perturbations in general. Okay. First of all, this is only perturbation y, but it's not hard to see that you can perturb y keeping the condition on x the same. So essentially, I can perturb the distribution on xy such that the margin on y, if I take the margin on y, it saturates this Imax epsilon. Okay. So did you get what I'm saying? So I want to perturb y. So I'll perturb from Py to, let's say, P double prime y. And I'll take the conditional distribution of x given y to be the same as before, to be the same as. So that is a way of perturbing xye, keeping the correlations of x to y the same as before, but essentially only touching y. So that will be good enough for this. You can do a similar thing for this. So I will keep the conditional of y given xc the same as before. So these are three different perturbations. Is this clear to everybody? That you can indeed perturb xy.
Yep. Yep.
Yeah. Okay. Good. Yeah. Now, what I have to do is
Take an intersection.
Yeah. So take an intersection of three perturbations. So what do I mean? So these are three different perturbations, but to run the proof, I have to work with one state, right? So the actual proof that I do, I will not. So for these individual states, I will not be working with P, but I'll be working with a perturbed form of P. But which one to use? P prime, P double prime, P triple prime? So the answer is no. I have to take the intersection of them. So I have to work this proof out with. So work with P hat xi yj instead of E xi yj. Okay. Now this is the intersection. So what do I mean by that? P hat of xye is defined to be the minimum of P prime xye. So this is the perturbation for R1 plus R2. Then P double prime of xye. This is the perturbation for R1. And P triple prime xye. So this is the perturbation for R2. Okay, so this is the perturbation for R1 plus R2. This is the perturbation for R1. This is the perturbation for R2. Okay. So the three different perturbations, but just take the minimum or the intersection. So intersection, because I mean, if you think of probabilities as concentrate on some subsets, this will be the intersection subset. Okay, so I mean the probability is 1 if the point lies in the subset, if it is 0 outside. So if those are the probabilities you are thinking of, then this is the intersection subset. But more general, this is the fuzzy intersection, as in fuzzy set theory, so the minimum. Okay. Now I know P prime, P double prime, P triple prime, where each epsilon close in L1 to the original distribution P. What about P hat? Same argument as before. You apply triangle inequality. So P hat is 3 epsilon close. So not epsilon anymore, but you pay a price 3 epsilon close to. Not a big deal. So now do this whole proof with P hat and then all these operator inequalities. Okay, so the key part was these inequalities. So they'll go through as it is with the smooth quantities because I'm working with P hat. Okay, the proof is
precisely
done.
Because P hat is a minimum. That's what forced the intersection.
Yeah, that's what forced it. So finally, I will end up showing that the convex split state with P hat is close to the fully product state. So I would have ended up showing that the convex split state, but here I'll have a P hat close to the fully product. But then I apply one more triangle inequality at a price of 3 epsilon. So change this P hat to P and hat. So that would finish the proof of the tripartite convex split lemma. And again, the same way, like let us say X and Y are independent random variables. Then you just look at, rewrite the convex split state in terms of our covering language, which we did for unipartite. That part of the proof is the same. And we will prove the tripartite covering lemma that we wanted out here, that I wrote here. So this is what I'll call the tripartite covering lemma. Covering lemma, and it just follows as before by like re-expressing the states in the tripartite convex split lemma. So we are done with this, and okay, I've taken more time, but so I should stop. So anyway, so with this we are done with classical one-shot theory. From next time we will start quantum information theory. We'll start from the basics, and we will see the similarities and differences as we go on. But once you have solid grounding in this, a lot of things will be very similar. Okay, and things should look fairly intuitive. But the reason I emphasize this intersection, and Shantanu is saying intersection is this part of the proof. Okay, so the tripartite convex split lemma, exactly the same proof will work in quantum. Okay, with quantum states instead of probability distributions. So you can prove the non-smooth part exactly as before. Then the hard part is if you try to prove the smoothing, the question is what do you mean by the minimum? So here we said intersection minimum, and we got away with that, right? So, but yes, where was the minimum? Yeah, so this minimum. So it is that thing, it is this concept which you don't know how to do in quantum. We don't know how to take this pointwise minimum in quantum. And this is what is known as the simultaneous smoothing problem. Okay, it's a big open problem in quantum information theory. And there are ways to get around it in some cases, but the general problem is quite open. Okay, I'll stop now. Any questions, doubts? No? Okay, so I'll put up the lecture shortly on YouTube, and see you on Thursday, and thanks for attending on a holiday. Bye. So Aditya, you can stay back.
Yeah. I think Aditya
should be there, right? So catch hold of.
But Pranav, so are we doing the other proof also, or just the presentation?